In this video, let us see an activity. Sin I by sin R is constant. So for that, what I am doing is I am taking a pro circle and I have taken a white sheet and I am marking the degree from 0 to 360. So I am naming the numbers. I am giving the numbers from 0 to 360 degrees. And I am bisecting the circle to the middle of the circle. And I am drawing a normal here at the 0 degree. This is a normal. I am naming it as N and N dash. And down also consider a normal. I am naming it as M dash. So these two are the normals now. And on the bisecting line, I am placing the semicircular glass slab. So after placing the semicircular glass slab, what we have to do is we have to incident a light ray by using a laser light. Here I am incidenting a light ray by using a laser light at between 10 and 20. That means 15 degree. So the light ray will enter into the glass slab and it will refract from the glass slab. And here we can observe that the ray which is refracting out from the glass slab will bend away from the normal. Here we have taken a normal M dash. So the light ray is bending away from the normal M dash. So whenever we are increasing the incident angle, the refracted angle also increases. And here the incident angle is taken as I and refracted angle is taken as R. In the same way, we will consider sin I and sin R. And finally, we will take the ratio of sin I and sin R. So this table we will consider. And we can observe that the ratio of sin I and sin R values will be same. This is an activity to show that the ratio of sin I and sin R is constant. Hans Christian Ørsted is a scientist who demonstrated that electricity and magnetism are not two different sciences, but two are interconnected sciences with an experiment in 1820. In his experiment, he placed a compass needle underneath a wire and then turned on electric current. The needle of compass showed deflections. A needle of magnetic compass generally shows the direction north and south. If no other forces influence the needle. If a bar magnet is brought near to the magnetic compass, the needle will deflect according to the movement of the bar magnet. Here you can see very clearly the movement of the needle is moving according to the bar magnet. That means the bar magnet is influencing the magnetized needle in the magnetic compass. Take two batteries and a magnetic compass and a copper wire. Now connect the wire to the battery. We can observe the deflection of the needle of the magnetic compass. The connection is removed. Again the magnetized needle come to north and south direction. And now change the direction of the batteries and again connect the copper wire to the batteries. Now you will observe the deflection of the needle in a different direction. The direction of the deflection of the needle also changes as the direction of the current passing through the wire changes. Here there is no bar magnet, but the needle is deflected. It is influenced by the current passing through the copper wire. We are going to have a look on an activity, refraction through a glass slab. For this, the requirements are the protractor, pencil, pins, scale and glass slab. And a white paper. This white paper is placed on a thermocol sheet actually, or you can use a wooden block, and I'm pinning it such that the paper won't move. And now I have taken the glass slab, rectangular glass slab, and I'm drawing the outline of the rectangular glass slab. So this is the outline of the rectangular glass slab. Now I am placing a protractor at the top of the out layer of the glass slab, and at perpendicular to the glass slab I am pointing now. The line perpendicular to the glass slab is our normal. This is a normal. This is our normal now. And now again I am taking the protractor and I am taking the angle by placing exactly 90 at the normal. (90), 10 degrees, 20 degrees, 30 degrees. So this is the 30 degrees angle, and now I am drawing a line to the normal. So this is our incident ray. This is our incident ray. I making an angle 30 degrees to the normal. It is making 30 degrees angle to the normal. Now again I am placing the glass slab, and here what we have to do is take two pins and place the two pins on the incident ray. We have drawn already the incident ray. On that incident ray I am placing the two pins like this. Now by seeing the two pins through the glass slab, as if they are straight, I have to place two more pins. See, now the two red pins are straight. Apart from that, by looking in through the glass slab, I am placing two more pins, green pins, and these pins should be also straight, should be in straight line. So the two red pins and two green pins should be in a straight line. So by looking into the glass slab, I have placed two pins also here. They are in straight line. And now take out the glass slab, take out the two pins, green pins, and now join the two dots where I have placed the pins. Join the dots to the glass slab. Yes, so this is our emergent ray, and this is the point of incident on the glass slab. So I am drawing a normal there. So this is a normal, and for the incident ray at the point of incident I draw the normal again. Now these 2 points, the incident incident ray and emergent ray, both the 2 points I am joining, and I am extending the incident ray. See, incident ray I am extending it. See, this is our extended incident ray. If the glass slab is not there, the light ray have to pass through this extended incident ray. Due to the glass slab, here we are getting the emergent ray, so the distance between this emergent ray and extended incident ray is our lateral shift. The shift is lateral shift, and here we can observe one thing. The light ray is traveling from air to glass, so it bent towards the normal here, and after that it is traveling from glass to air, so it is away from the normal. So if you measure the angle here, incident angle we have taken 30, so the emergent angle should be also 30. If 30 not comes, we may did some experimental error, that is due to pressing the pins. By looking through the glass slab, we may have done an experimental error. So here I got the emergent ray angle is also 30 degrees. We can check it by the protractor, or we can check it by incidenting a laser light on the incident ray. If you incident a laser light on incident ray, if the emergent ray comes through the emergent ray we have drawn, then we have done correct. So let us check that by incidenting a laser light ray on the incident ray. See, here I am incidenting a laser light on the incident ray. So the light ray is emerging out on the emergent ray which I have drawn. See, yes, the light ray is emerging out from the emergent ray which I have drawn. So what we have done is correct. So this is an experiment. The refraction made by a glass slab. In this video we are going to do an activity about the reflection of light. We know what is meant by reflection. The rebounding of the light when it is entering into other medium, it comes back to the same medium due to the a shining surface, or due to the effect of the second medium. Rebounding of the light is called as reflection, and in this video we are going to do an activity basing on laws of reflection. We know the two laws of reflection. The first law is the incident ray, reflected ray, normal. All these rays lies on the same plane. The point of incident, the point of reflection, and the normal point. All these 3 points lies on the same plane. And coming to the second law, the angle of incidence is equal to the angle of reflection. So these two laws we are going to do in an activity word. So let us go to the activity. This is the experimental setup which I have taken. Here 0 degree is the perpendicular line to the mirror, and this is the perpendicular, and this can be considered as the normal. So when the light ray is incident to the normal, we can't see any reflected ray here. So the incident ray will be the reflected ray. So there will be no angle of reflection here. The two rays coincidence. with each other. Now I have just changed the angle a little, so now you can observe a incident ray and a reflected ray. Now the incident ray is at 10 degrees and the reflected ray is at 350 degrees. So the difference is incident ray is 10 degrees, so the reflected ray is also 10 degrees. If the incident ray is making an angle 20 degree, the reflected ray also will make an angle 20 degree to the normal. You have to measure this angle to the normal, from the normal. So if the incident ray keeps on increasing, the reflected ray also will increase. So by this we can say that the incident ray angle of incidence is equal to angle of reflection. And here you can observe the first law also, the incident ray, reflected ray and the normal all lies on the same plane. So the point of incidence, the point of reflection and the normal point all lies on the mirror itself. And here to get the rays, I have made an arrangement with dope sticks. So if the smoke is more, then only you are able to observe the rays very clearly. If the smoke is less, then we may not see the rays clearly. So if you make such arrangement, you see that there should be a lot of smoke. Then you are able to see the rays very clearly like this. So if the smoke is very less, then you may not observe a ray. It may be somewhat blurred as you seen before. Now it is a sufficient smoke is there, so you are able to see the rays very clearly here. Thank you. This is an activity based on a reflection of light. The image in a plane mirror using a glass plate. Here we are not using a mirror, we are using a glass plate, and this is the experimental setup. Here we have to place a lighted candle, and in middle we will place a glass strip, and after that we will place a unlit candle, and these candles should be placed at the distance of 15 to 20 centimeter from the glass. So what happens is, when we place the candle 15 to 20 centimeters from the glass, see, we can observe the image of the candle on the glass. As it is completely dark and only one side it is lightening, we can see the image of candle on the glass. Here the glass acts as a mirror. From other side you may not observe that. Yes, from the lightening candle we can observe that the image of the candle in the glass. So by adjusting the unlit candle, other side of the glass we are having an unlit candle, so that candle we have to adjust by moving front and back. So by moving the unlit candle front and back, we can observe the flame appearing on the wick of the unlit candle. Here I have measured the distance and I have taken it. The distance between the lighted candle and the glass strip is 15 centimeters. we have to record that distance, like from the glass strip to the candle which is lightened can be taken as object distance. Here the lightened candle is the object and unlit candle can be considered as an image here. So the distance between unlit candle and glass strip is the image distance, and the distance between a lighted candle and a glass plate is the object distance. So when we can see the flame on the unlit candle, when these two distances, for example, the distance between the lighted candle and glass plate is 20 centimeter, then the distance between the unlit candle and glass plate should be 20 centimeters. Then only the flame can be seen on the unlit candle. And if the distance between the lighted candle and glass plate is 15 centimeter, then the distance between the unlit candle and glass plate should be also 15 centimeters. Then we can see the light on the unlit candle. So by this experiment we can say that the object distance and the image distance is same. In a plane mirror, the object distance will be equal to the image distance. So both the distances are equal, and we know that, and the size also can be considered as same. Whatever the size will be there for object, the image also will have the same size. And mainly here we can observe that the object distance is equal to the image distance. If the unlit candle moves away from such distance, we may not see the lightening on that unlit candle. So this is an activity about reflection image in the plane mirror by using a glass plate. And by using the glass plate, and these are my observations. When the object distance is 20, the image distance is also 20. When it is 15, it is 15. When it is 10, it is 10. And when it is 5, the image distance is also 5 centimeters. Hot air is lighter than cold air. Take 2 paper bags or empty paper cups of the same size. Take a broomstick. Hang the 2 bags in the inverted position on the 2 ends of the broomstick. Tie a piece of thread in the middle of the stick. Hold the stick by the thread like a weighing balance. Put a burning candle below one of the bags. So we observe that the balance of the bags disturbed. This is due to hot air in one cup and cold air in another cup. Hot air cup raises up while the cold air cup comes down. By this we can say that the hot air raises up. Take a balloon, blow air into it. As we fill it up, it expands and it becomes harder to press the walls of the balloon. The inside air exerts pressure on the walls of the balloon. Open the mouth of the balloon slightly. Air from the balloon comes out. You can open the mouth less or more and control the flow of the air. The air in the balloon is at high pressure and it goes towards low pressure area, means outside. You already know that when air moves, it is called as wind. Air moves from the region where the air pressure is high to the region where the pressure is low. The greater is the difference in pressure, the faster the air moves. We still have to think why winds occur in the nature. Take an incense stick or doop stick and light it. And here we can observe the smoke rising up. It is important to remember that on heating the air expands and occupies more space. When something occupies more space, it becomes less dense. The warm air is therefore less dense than cold air. Thus, smoke and hot air goes up. When the air raises up, air pressure at the place becomes low and we have many kinds of winds as air comes in to occupy areas of lower pressure. The differential heating of land and water by the sun leads to land and sea breeze. The land heats up faster than the sea, so warm air rises over the land during the day as it is warmed by the sun. At certain times of year, this can create a sea breeze, which is a gentle breeze blowing into the land. At night, the land cools faster than the sea, reversing the airflow. This creates a land breeze and this video we are doing an activity regarding the magnetic field. For that, what we have to do is we have to take a white sheet, and that white sheet should be placed on a table, horizontal table. And now already we did that, so place a bar magnet at the middle of the white sheet. Yes, we placed a bar magnet at the middle of the white sheet. And now take a magnetic compass and place the magnetic compass near to the bar magnet. Now we placed a magnetic compass near the bar magnet. So if you see the needle will deflect according to the bar magnet. So now it is at rest. So we have to put dots at the ends of the arrows. At what direction the magnetic compass is showing, there we have to put 2 dots. Now take the magnetic compass and join the 2 dots and put a arrow mark, because this is south, this is north. So at north I am placing an arrow mark. Now take the magnetic compass and place at another position. So now again it started deflecting and it will come to rest at one place. So at that place we have to put the 2 dots. So this is south and this is north. So again join these 2 dots. This is south, this is north. Now in the same way, place the magnetic compass in another direction, in another place. Change the position of the magnetic compass. Now again the needle is deflecting. The needle is deflecting. Now the needle come to rest. So again put 2 dots. And now this is south, this is north. Join the 2 dots and at north you put a arrow. Like that, here also we are observing this. Again the needle is deflecting and needle, yes, it came to rest. So again put 2 dots. Now join these 2 dots, and this is north, this is south. So if you observe the arrows, they are in different directions. Why that the direction of the arrow changes? That is due to effect of the bar magnet. Now here we are seeing the position of the magnetic compass. Now it is showing the north and south direction. The needle is towards north and south direction. Now observe what happens when a bar magnet is placed near to the magnetic compass. Now I placed a bar magnet near the magnetic compass. So now it is not showing north and south. The needle is deflected according to the bar magnet. So the magnetic compass needle is affected by the bar magnet. Now if you move the bar magnet away from the magnetic compass, now see what happens. Again the needle is coming to rest in its original position. That means north to north and south. So this influence is due to this bar magnet. That means this bar magnet is having some field around it. So due to the field around the bar magnet, it is influencing the magnetic compass needle. So due to that, the direction of the magnetic compass is changing. Thank you.